So tomorrow I have my Viva for my PhD, 3 years of work, almost to the day. Incredibly arduous and focused period of my time where I've basically tried to completely break down the VR render pipeline, improve it via new methods, improve the interaction that exists currently with Ray, which is the laser pointer. And then I move into how I've developed this interface, which is kind of supporting future modalities, and I'm very confident in its adoption at some point. And whether or not Meta eventually or Steam eventually introduce this into their accessibility menu is a matter of time, not if, in my opinion, which is reassuring. I'm very confident in it, and I think from everyone I've spoke to, they've been really interested in it, but they could have been lying. But I think I've been drinking from my own Kool-Aid for too long. So the presentation itself is really long, but I'm only gonna have the actual presentation going over the first 10 slides or so, and then the other decks or slides I've made, sorry, I've just been for discussion. So if something comes up during the presentation, or the Q&A section, I guess, I'm able just to go to the slide and discuss it in a little bit more detail. So first of all, this is what we have. I'm gonna have to go into display settings and duplicate slideshow. If the system doesn't glitch, to which it appears it did, but that's okay. So, optimizing for holistic VR interaction. The thesis, yeah, so I'm going to go over the overview really briefly. We're going to discuss the problem, or the problem question that was asked at the start of the PhD. And then the two main key findings. There are numerous findings within this, but there are two key points of discussion that I wanted to make, and the methodology and the results from these studies, which have quantitative, actionable feedback we can use to iterate upon for future projects. So, firstly, I wanted to go into a little bit of the emerging fields and where VR is going just now, or what other technologies are exploiting some of the discussion points that have been made that wasn't explicitly mentioned. This lady is called Vernda, or Vandy, I believe, and she is a scientist at JPL with NASA. Every day she receives telemetry from the Mars Curiosity rover about its position, and she has to map out where the rover is going to go next. And she's using a stereoscopic 3D glasses here on a 2D monitor in order to understand the depth perception of some of these rocks that the rover could hit, obstacle avoidance. We're trying to deter any injury to the rover itself. As we can see here, that this is actually going to be used for a real project that's existing just now, and without it, then we don't have the depth perception to make accurate decision making for the rover itself. So it's an extremely highly sensitive area of work that requires the use of a depth camera. Another area is the Valkyrie NASA robot here. We can see a lot of human ergonomics are related here. So again, we're almost reverse engineering the human in order to make a humanoid, which we can then remotely dial into using a VR headset and then interact with buttons, as we can see here on the left, and also do basic tasks that we would do in reality, which with minimum ease. But as you can imagine, as latency is reduced, you'll be able to have humanoids that are either controlled by AI or using a VR headset in a remote environment. You know, health and safety. You can see how this is going to be extremely good for something like that once the robots are nimble and real time. Another area is Sanctuary AI. This is one of my favorite kind of exploitations of the VR devices. What we're seeing is, again, a stereoscopic cameras at the top with the Azure Connect DK, which I used for numerous experiments of mine. And the robot is designed, it's not really focused on walking, it's primarily focused on doing human-based tasks with hands. What we can see here on the right-hand side is the Valve Index HMD being used with some haptic feedback gloves, which track all fingers. And from this, we're able to control the robot in the same way we do. So with minimal latency on the same network, it's actually going to be quite a viable product for doing extremely repeatable tasks in a factory, for example. The interesting thing about Sanctuary AI is they actually use the data trained from the VR headset and the gloves, and also a couple of reinforcement learning in synthetic environments in order to train how the AI is really going to pick up objects and it uses the Unity engine, I believe, for this, or it might be using NVIDIA's now. But it's an interesting concept to see how we're using hand tracking more. So regarding visualization techniques, one of the points I made in the paper was that scientists are left from different fields looking at data sets on traditional 2D. And this is what it looks like for neurons inside of a tadpole's spine. Obviously, a professional and someone who is extremely familiar with the graph will be able to isolate patterns and see nuances that are relevant to their research, or they'll be breaking it down via a filter, and then they can isolate exactly what they want to look at. But that doesn't really allow us to have a holistic view for the average person to understand and perhaps have some spontaneity and insight into the data set. So what we can see here is the exact same information represented in VR, where the spinal cord is now isolated at the top, and you can see more information that you might be able to make more heterogeneous kind of associations with other bits of information and metadata if you know more about each individual neuron. So this is just a point that I want to make, that the applications of visualization in VR are not exclusively for entertainment or historical preservation or digital twinning. What we're really seeing is some real life use cases where we're able to be inside of the data set itself and explore data in a way that we haven't done before. So from the start of the PhD, it was, the stipend was to improve insight and engagement using immersive tech. So what does this really mean? Insight is through visualization, and engagement is through how we interact with the data or the environment that we're presented in. So this really raised the question, like, the engagement section is where VR is not as high just now. Visualization, we can render 3D models and spatial temporal data. We can also render vector fields, scalar fields. Any type of 3D data set is relatively straightforward, point cloud, to render in a 3D environment. But the engagement part is how can we make associations between other data sets and how we can actually interact with the data itself. So how do you actually do that for VR? Well, it's about presence. What does VR provide that 2D monitors don't? And it's the sense of presence. So in order to have a sense of presence, there's many systems that we have to acknowledge and exploit in the human, where our optical focus distance, what is the range of motion we have as an able-bodied person, what are the limitations for a non-fully able-bodied person. So we need to acknowledge the player or the user inside of the world. And this was from Valve, Newman, he basically said that the world needs to acknowledge you, and I couldn't agree more. It's exactly a wonderful sentence to say that the world needs to acknowledge your presence, and then you feel engaged because it's reacting and it's responsive. So what can really be improved? Well, engagement also means interfaces, maybe. So if we look at the current history of interfaces, we started a punch card almost 100 years ago, command line interfaces, graphical user interfaces, spatial computing in 2010, where we're able to, start getting VR headsets on the market. And now in 2020, we're actually looking more into natural language, brain-computer interfaces, and hand gesturization, which is part of spatial computing. So you can see the trend is going this direction. So I wanted to kind of exploit this era from 2010 to 2020, taking lessons learned from the previous generations of interfaces. So the first key finding I want to go over is the tremor reduction. So the majority of interfaces use array, and this is the laser pointer. Everyone has tremors, which are between the range of 4 and 12 hertz, really, because some of the ailments are not. But it is psychotic tremors, yep. So what we want to do is remove tremors from existing interfaces. I wanted to first solve some problems that exist in current interfaces, but also is backwards compatible, being that any interface that uses array that has already been developed, this solution is an algorithm that we can place between the user and the software development kit or the OpenXR standard, and then we can filter out tremors using the 1 euro filter. So first of all, I wanted to prove that the 1 euro filter works in Unity. Very simple exercise, which allowed me to basically see that yes, there are tremors that we can simulate, and we can also normalize them. So Tableau dashboard, temporal data here. What we can see is the red is the filtered noise, and then the blue is the noise generated. So the cube is just moving in a sine wave function. It's vibrating as it does it, and we're recording that information. But then we're also recording the same point in frame at 50 frames a second using the fixed update function. What we're able to see is the normalized input. So you can see it is normalized. It looks much smoother, and there was no change apart from real-time updates. So I needed to prove this in a user study. It was a repeated measures within subjects kind of study, because there is a control group in the data set. So we have But what I wanted to do was see exactly how users interact with both. So if I had two separate groups of people, then they're not necessarily exposed or familiar to VR. So I wanted to group them together. So to control for measures, I did a 50% randomization on when the filter was enabled or disabled for their first pass through, because I wanted to counteract users learning or gamifying it once they understood how they're moving the laser and selecting buttons. So again, this is a general population of, some people have tried VR, some people haven't. It's just a general overview on how VR interaction is. I don't know if I had anyone who really did not try VR at all in the study. Actually, no, everyone at least tried it once or twice, and this is an important aspect that I wrote about in the paper. This is still in review. 5 rejections or so, but it's a very, it's a critical it's something that I see every VR interface will eventually have or adopt via the accessibility menu within Meta or Valve or any other HMD manufacturer. I believe its adoption is inevitable, and it's just a matter of time, so it's quite cool to be thinking of that. So users would be tasked with entering 4 numbers and then pressing stop after start, and then they would move from 1 to 5 to 10 meter ranges, and then they would have a slider, and they do the same for the slider. So we're looking at buttons and sliders, which are really what everything's made from. So just to give a brief overview, because the paper obviously goes into this in much more detail, where we use a p-test evaluation to compare two sets of demographics, or 2 sets of null hypotheses where we have the filter on and filter off. We can see that there is a trend to it being quicker and much more normalized in distribution for ranged tasks, and also we're looking at a larger distribution in people's time to complete the task for selecting the slider. 0.5 seconds for 1 meter, not significant really. 4.11, pretty like, it's an average improvement of 4 seconds. That's 1 to, it's pretty quick. And then obviously 11 seconds for 10 meters is quite significant. But some of these, using a p-test evaluation, only 50% of these show significance. As you can see here, we're seeing significance because the standard deviations don't intersect, don't intersect, 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 don't intersect. So 1, 2, 3. The slider was actually the biggest benefit from this one. And you can see for 5 and 1 meter range tasks and buttons, it didn't do it too much, but there is still a statistical improvement for some people. And that's the most important thing, is that this filter is in real time. It's a low pass filter. It allows you to move quickly and the filter is disabled with a delta cutoff value, but then if you move slowly, the filter is enabled. So empowering the user. Oh, crikey. Hello. Hi, speaking. So, based off of this, we're looking at the problem of we're currently interacting with the VR. So I've tried to improve, currently interacting with VR with laser pointers. So I've tried to improve that for every VR interaction. And if we look at how it's currently being adopted, we can see there's a little bit of tremors here, and no filter here. This is using the Half-Life Alyx, and you can see it's a 2D panel with windows and context buttons. And at the bottom right corner, we can see game developers using their, implementing their own unique design mechanic to work for their design. Games are meant to be fun, and this is exactly what they've done. But it does lead to an accessibility gap where perhaps users who have asphyxia, who can't rotate their wrists, or their hands are going to be tremoring, which prevents them from using this. And this is something that maybe we should consider. What is it like to make an accessible interface if you're trying to accommodate for users who potentially have long-term or short-term accessibility issues? So from this, I wanted to look into, okay, so if we're going to use hand tracking or something more natural, I want to exploit our proprioception ability if we don't have any familiarity with 2D interfaces in VR. Which is currently what it does. Using a laser pointer is very akin to that of a traditional cursor or a button press on a iPad or something like that. It's a very intuitive interface. We're all used to it. So is there anything we can exploit from our understanding of reality that we can use for a new form of interaction? And that's where you get into natural interaction and heuristics and so on. So I developed a short prototype using Kajiro's training model for hand tracking. And I went through this a couple of times with my own data sets as well, so which proves a good point of concept for like future studies and future work, and being able to integrate and train my own AI into the Unity Barracuda inference engine. So this is real time. This is in 2021 though, and Oculus Quest did not have hand tracking at this point. You know, it wasn't largely adopted, but to me, this experiment showed that we can get real time accurate hand tracking in 2021, meaning it's probably going to have hand tracking very soon in VR, and it would be very cool to implement an interface that uses this or considers it at the start of the implementation stage, where we're focusing on an accessible first design philosophy to kind of revolutionize or change the way we interact with VR if we're not using a laser pointer. So this is where the modular 3D interface came into. I wanted to empower the user to choose where they wanted to move elements, and basically do a small focus group which would understand where are the pinpoints of innovation, or the points where perhaps don't have a high usability satisfaction. So in order to do this though, I needed to consider about how humans move, or ergonomics, anthropometrics. There's a lot of data on this in the paper, but to be brief, it was important to see how far away we can see information and what's our depth perception in VR. And the formula there allows you to get an estimation on what is the depth perception for a current HMD given its field of view. And the interpupillary distance, it just basically allows us to calculate our current depth. It's a very, to be honest, it's not really that critical when you understand that fixed focal lenses on HMDs just now are currently at 1.3 because we don't have varifocal lenses. So it's 1.3 meters is when you're in super clarity, but everything falls off after 20 meters. Given the graph on the right, which is very rudimentary, I do apologize for that, but it is taken from data from another chart. Alex Vechos in his Google talk with Samsung. So the comfort angle for horizontal movement range, meaning that where is it comfortable for us to rotate our heads while wearing a cumbersome HMD. So we're looking at distance and movement ranges and stuff, and all of this information can be put onto a single graph, which we can say this is where users want to interact with, this is their personal space, and this is where we can see good 3D depth estimation. And also we have the visual limit on the right eye on the left and the left eye on the right, and this basically means that if you close one eye just now, you actually have, you know, your peripheral vision going off this way, and that's kind of roughly where it is based off of a couple of papers focusing on, you know, anthropometrics. Well, not really anthropometrics. Anthropometric side of things really come into the head rotation and reach. What we're really looking at here is visual perception limits, which are found in numerous journals that I didn't expect to be reading for this, but very interesting stuff. So in order to make this interface, now we understand where we should put elements, and we're looking at a hand tracking, so I need to think about that. I scraped all EV chargers around Scotland over a 6-month period at 15-minute intervals, represented it in Tableau. All the information was JSON, very messy, no logic to the structure, to be perfectly honest. So I scraped it over time, actually using a PowerShell script running for actions tasks on Windows, because why would I do anything else? It's an extremely efficient way to get the information on my system. And then I put it into a SQL database and hosted it on the cloud. Went around with the Azure Connect DK and recorded a variety of chargers and associated it with each geospatial point, which allowed us to represent the information in VR on this 3D topographical map. And you can see the start of the interface being developed out here. And on the right hand side here, you can kind of see what it was like in the lab environment. And there's a 3D video there of a car being like scanned, although LiDAR is ideally used for humans or depth estimation in dark environments. Photogrammetry is the way to do this, really, but I had the Azure Connect DK and I wanted to try and innovate with that piece of technology. So this is a proof of concept kind of thing, but it kind of worked out, and this is the architecture if anyone's curious. So the key concepts of the modular interface is that it's powered by the physics engine, meaning that it is akin to that of reality. We'll be able to predict, and we'll be able to see exactly what elements will be interacted with when you interact with it yourself, being that two physics bodies will bounce off each other, you will bounce off of it as well. The kinematic panels, where the borders act as buffer zones, and the contextual based user environment. So basically where the interface is being displayed is very important to what is the task that the user is trying to complete at that specific point in the digital space. So the kinematic panels have borders which act as buffer zones, which allow for the user to grab the panels and manipulate them around the environment and place them wherever they want to, without pressing on the buttons accidentally, or so it's meant to. The design kind of started off as that of a clipboard. I always thought people could use one hand and then type with the other. But then the reality was, why are we doing that? Because you might be left-handed, meaning I need to have 2 white lines. But then what if they want to grab from the bottom? So then I just made the panel all the way around it. And the slider was a really fun exercise to complete, really, because I started with a 2D slider at the top, thought about it, made it as unrestricted as possible in a 3D environment with a spring moving all the way around. And then I added constraints to it. And then I considered maybe, it seems a little bit annoying if you move it this way. If you move the slider to the side and you go to grab it again, it might move again, because just the specifics and the nuances, especially if you don't have the €1 filter enabled on your hand, which is something that I've been exploring. And the €1 filter with ray-based interaction is great, but it can be used everywhere. I think it should be on everything, to be honest, because there are noisy signals being produced by hand tracking anyway. Just from the nature of the headset and using vision-based approach. But what we're seeing here is the sliders being anchored back to the center after you interact, meaning it's more like a scaling. You're going up and down. It's very similar to that when you press the middle mouse click and you have the scroll moving when you move the mouse up and down. So the focus group targeted intermediate to novice VR users, and basically the usability satisfaction highlighted from positives here. It was little movement to zoom into the map. It was having the UI follow you around the environment was satisfying, and also being able to select which hand you want to use was quite liberating for users. So I'm now just going to go into the demos. There'll be 2 demos, maybe 5 minutes each. There's an accumulation of all the graphics that was developed for the thesis itself and the paper publications. But actually, they're just numbers and statistics. So then when I put it into a 3D environment, I can visualize it. And that's what I've made this demo for. It's completely downloadable online. So in the description, I can put a link to that, or put it on Steam at some point, perhaps. It's just, 6 little VR museum that might teach you something about yourself. And then this is where the penultimate thing really came to prior to the Viva, was that now we have hand tracking with the Quest. And this is something I predicted in 2021 that we're going to get soon. I didn't expect it to work so soon, but it allowed my interface to be interactable using hand tracking with gestures. So what we're seeing is like a full end-to-end solution of a new interface that has a multi-model interaction approach. It works with eye tracking, fire an array from your eye, and because everything's using like the observer design pattern, like an event-based system in Unity, every entity here can be fired by an event of whatever you want. You can use voice to trigger the arrow keys, and for me it was just it's a really nice way to immerse yourself in a digital space. And with mixed reality coming in, you can see here it's working with hand tracking in mixed reality, and I have an AI agent walking around here. So like the technology here is really quite cool, and there's many design decisions around like the color schemes, the why am I having 3D objects floating around my lab. There's a significant amount of design that's went into this. That's actually, I would say, some of it's based off of intuition, but it's initially based off of intuition, but then there's a reason for it. So the reason we have floating objects is because we need to have a sense of depth in the world. It's really kind of pointless having this world if everything looks 2D. So having these things floating around gives context to your depth more, like you do in the real world. You have 3D objects everywhere, so you can interact. And for the rest of this, these slides I'm not going to really show. It's just for discussion, basically showing how, light from reality goes into a camera, which is then projected onto a display, which is then put onto your eye. That's a 3-step process, meaning we're recycling photons to the display to your eye. But then if we're using waveguides, it's only, stages 2 and 3 really, where we're just displaying it and it goes to your eye. Because we're just using the cameras to track your environment. So that's why augmented reality and mixed reality are different, and one recycles photons, the other doesn't. You can think about the process and limitations there, but this is interesting if you're interested. It's basically about like there are myths in human perception. We see about 1,000 hertz and maybe 750 people said, but in my opinion it's over 1,000 hertz. 0.03 milliseconds is what people have seen a single frame in a 144 hertz display, I think, in a study I read recently. But yeah, I mean, we're looking at biology here and light, and we're not looking at a computer system which is laggy and doesn't have any survival traits associated with it, but evolutionary we do, meaning quick reaction time. So then the finding 3 here, which is I'll discuss briefly, is about my frameless eye-tracked foveated rendering solution, which allows you to use frameless rendering within the VR pipeline after rasterization, before fragment shaders, I think, is where it's going to be. In essence, we use nitride foveated rendering, being that wherever you look is a higher resolution. But rather than waiting for the entire frame to process and then being displayed to the frame buffer, what we're going to do is just put the pixels at where the user's looking as soon as they're processed. And what this means is if we have a missed frame, meaning that it's taken too long for a computation and a vsync cycle to complete, rather than skipping a frame, which is jolting to the user, we're just going to skip the pixels that have been missed, which means that the user might not actually even acknowledge it. And yeah, there's just control system theory, some of the extracurricular, I would say, various studies. I worked with museums, highlands and islands to develop a 3D photogrammetry website for them using real time with a little app I made. It works for mobile. That's an environment study that I did. And I've put headsets on every single demographic I can think of just now. Non-expert users, expert users. Aging demographic was an interesting one. Users bound by wheelchairs. So it's an extremely interesting area of research that I am excited to pursue after a good night's sleep. So I hope this was relatively interesting to everyone. It's very, very informal. Go on my website, scroll around, click through it. Hopefully you find it interesting. If anybody wants to talk about it, I'm here for it. Implement it. Call me out on crap. I don't care. But the idea is I'm going to release this into a book. I've already started narrating it. I need to get the cover done and I can deploy it onto Amazon after Springer accept my paper. So, and if Springer don't accept the paper, I'm just going to release it on archive standard and just wait for it to be adopted, and I can be like, haha, I did it. Right, but yeah, no, my emotions just now are weird. I'm exhausted.